Okay, let's see. For simplicity, let's consider the case of an electromagnetic field in a vacuum. Vacuum means there is no presence of any charge. Okay, no current, no charge, just nothing. Okay, there's no charge anywhere, no source, no rho, no I. Okay, how does one write Maxwell's equations in this case? Well, there's no rho, so this is 0. This is always 0, no matter what. And this is the Faraday's law. It's still the same. And as far as the last one, the Ampere-Maxwell's law, there is no current I, but don't forget we have this new term here, right? This displacement current, which is partial t, and that one still exists. So you have that term. Okay, so this is the new term that Maxwell added. So in a vacuum, you will have a set of differential equations like that. Okay, let's see what kind of solution can exist when we solve these differential equations. Okay, first of all, if this term did not exist, okay, if Maxwell never discovered the displacement current term, then, that means that if you look at the magnetic field, there is no longitudinal magnetic field because the divergence is 0, and there is no transverse magnetic field either because this term would be 0. Okay, how do you describe a field that's no longitudinal and no transverse component? Well, the only possibility for that field is just a universal constant. Okay, that field is just the same throughout the entire space. Okay, it's just a constant anywhere. Doesn't depend on time, doesn't depend on location. Of course, you take the any differential equation, you get 0. Okay, and same thing for the electric field. The electric field would have no longitudinal component and no transverse component either because the magnetic field doesn't depend on time. It's just a constant everywhere. So partial B partial t is 0. So there is no longitudinal component, no transverse component for the electric field either. So all we get, at the most, we get just a uniform electric field throughout the space that doesn't change with time. So without the Maxwell's new discovery, the only type of field that can possibly exist, electromagnetic field can possibly exist in a vacuum would be simply a uniform uniform constant field. Okay, a uniform constant field cannot possibly propagate energy. It cannot possibly transmit any power. It cannot carry any information from one place to another because it's always there. It's always the same and never changes from place to place and from time to time. That would be very boring. Okay, fortunately, we do have this term. Okay, and then what does the term do for us? Well, you notice that both of these divergences are 0. So in the case of a vacuum, the only possible field that can exist is a transverse type of field. Okay, longitudinal field is simply 0. It's a transverse field. Okay, and you also notice that these last two equations, there is E and B and B and E, they're intertwined in the same equation. Okay, so what I want to do is I'm going to try to separate E and B into different equations. Okay, into different equations. And how do I do that? Well, you notice that there is partial B partial t and here's gradient cross B. If I can somehow turn this side from B to gradient cross B, then I can substitute this in. I only have E, no B there. Okay, now to do so, I can simply take the rotation of both sides of this equation. Okay, so I have basically gradient cross E equals gradient cross negative partial B partial t. Agreed? See, all I have to do is take this equation, take gradient cross on both sides simultaneously. Of course that works. Okay, now at this point we would have to use a mathematical identity that you learned, or you should have learned at least in the math class. What is gradient cross E equal to? Okay, now some of you may recall. If you don't, check your math book, it's definitely there. This can be written as gradient dot E minus gradient squared E. Trust me, it works. Okay, this is the right formula. Now the other side equals what? There is a time derivative. There is also a space derivative. That's the gradient operator. time and space are independent, so I can exchange the two orders. I can write as partial t gradient cross b. Okay, now this is 0. This is 0 because of that. Okay, it's longitudinal field. So I have a negative sign that cancels out. So I have gradient squared E equals no negative anymore. Partial t of gradient cross B, which is right here. Gradient cross B is right here. I'm plugging in. Epsilon naught mu naught partial E partial t. Okay, I'm going to take epsilon naught mu naught out because these are just constants. I have to take derivative twice with respect to time. That's a second order derivative. So I finally arrive at this result. Okay, this equation, as you can see here, has only one unknown function. That's E. B is gone. Okay. Now the price I paid was that I had to turn a first order equation into a second order equation. There's, you have second order derivatives. And does this equation look familiar to you? Does this look familiar to you? Well, in physics 1B, we've learned something similar, except it was one dimension. We learned what's called a wave function, a wave equation. Okay. If the wave is described as y, and if it exists only on the x-axis, then I write something like this. Second derivative of y respect to space x equals what? 1 over v squared times the same second derivative, but this time respect to time t. That is the so-called wave equation. And if you compare with our case, all we have here is a three-dimensional extension of this wave function. This is a wave equation in one dimension. Okay, this wave can only propagate along the x direction. Here, this wave can propagate along all three axes. That's why you turn second derivative with respect to x only into gradient squared. After all, gradient squared is the sum of these three terms. Right? So, if we have all three, if it propagates in all three directions, then you have to, of course, change this derivative into the sum of the three. And so this really is a wave equation. Okay, it's a wave equation. It's a 3D wave equation. Okay, so we know that if we combine all these equations together for an electromagnetic field in vacuum, we find there exists a wave-like solution because we get a wave equation for the electric field. A wave-like solution. And what is the speed of that wave? Well, you compare. Here I have 1 over v squared. Here I have epsilon naught mu naught. So clearly, the speed of this wave can be written as 1 over v squared equals epsilon naught mu naught. Right? 1 over v squared, you replace with epsilon naught mu naught. But epsilon naught mu naught, both constants, they're universal constants. They're one of the few universal constants we've learned. So therefore, the speed that you're getting here is not just an arbitrary speed that can depend on the spring constant and all these trivial things. This speed depends only on a pair of fundamental constants, one for the electric side and one for the magnetic side of the electromagnetic phenomena. And therefore, this speed is also a universal constant. We use the letter C to stand for constant. So 1 over c squared must equal to epsilon naught mu naught. Okay? And I can solve for c then. C equals the square root of epsilon naught mu naught. And I know what epsilon naught is. I know what mu naught is. In fact, this was discovered separately by different people at different times. But you put them all together, okay, which Maxwell did for the first time. He put them all together, epsilon mu naught, numerically, and guess what he found? He came up with this magic number, 3.00 times 10 to the 8 meters per second. Now, I'm sure many of you can recognize what that number is. What is that? 300 million meters per second. That is the speed of what? The speed of light. Okay, the speed of light was actually already measured at Maxwell's time. So when he came up with this result, he knew that he just stepped on something very, very big. He had just theoretically calculated for the first time the speed of light. And therefore, this wave, the so-called electromagnetic wave, has the same speed as the measured speed of light. And what is your natural conclusion? Light is what? A form of electromagnetic wave. Okay, now this is huge, of course. This is just huge. So you can imagine Maxwell's excitement. He not only showed there exists a wave-like solution in free space when he added his new term, but he also found that the speed of that wave is a universal speed. It is equal to the speed of light. Okay, that is one of the greatest discoveries in all of science. For the first time, we understand what light was. Light was actually a form of electromagnetic wave. And we're going to study, of course, more of that in optics. Now, going back to this equation, it seems that when you look at this equation, you see, okay, I have an electric field which can propagate like a wave. There is no mention of the magnetic field at all. Actually, we substituted that. Does that mean that you can have a wave that only has an electric field, no magnetic field in it? In other words, something called an electric wave, okay, or something called a magnetic wave. Well, it turns out this is only an illusion. When we go from the first order to the second order differential equation, we have to take one more derivative. And you know very well that by taking derivative, you actually can lose something. What do you lose? You can lose a constant, right? So in going from the first to the second order differential equation, you could actually lose something. This equation only tells you E. It doesn't tell you B, but it turns out E and B are actually related. Okay, there is no such thing as a pure electric wave. There is only such thing called electromagnetic wave. It has both the electric and the magnetic component. You cannot live without one another. Okay, no such thing as pure electric wave or pure magnetic wave. Let's see. Before we study that, the connection between E and B components of the electromagnetic wave, we can also attempt to find an equation for the magnetic field. Okay, so I'm going to leave the details and exercise for you. See, what we did here was we got rid of B, okay, by substituting gradient cross B equal to this. I can do something similar. I can get rid of E first. What do? I can take the gradient cross on both sides of this equation. Then I get, on this side, I get gradient cross E, which I substitute as negative partial B partial T into here. I will then get an equation that contains only B and no E. Okay, and if you did so, you find they're exactly the same equation. Here is the equation for B. Same exact equation for B. So both B and E are wave-like. They have the exact same speed, the speed of light. Okay, and how exactly are they related? Why do I say you cannot live one without the other? They must coexist. Well, again, these are second order differential equations. I must go back to the first order in order to make sure I don't lose anything. Okay, so you go back to the first order, and here is, these are first order equations, this one and that one. Okay, you can see here, if you look at a case where there is no B field, okay, something called a pure electric wave, what do you really get? Well, there's no B fields, of course, partial B partial T is 0, okay. Then gradient cross E is equal to 0, but you see gradient dot E is also 0, right? Which means this is a field with no longitudinal and no transverse component, and once again, the only possible field for that would be just a constant uniform field. That certainly is not a wave-like field, right? So therefore, you cannot possibly support a pure electric wave without any magnetic component. And similarly, you can show that there is no such a thing as a pure magnetic wave with no electric component. As a matter of fact, it turns out in an electromagnetic wave, the E component and B component are totally synchronized. Not only do they travel at the same speed, they have the exact same phase, and their magnitudes are proportional to one another. You cannot live one without the other. Okay, to get to the details, we're going to begin by studying something relatively simple. Okay, of all waves, we study what's called a plane electromagnetic wave. Okay, so what is a plane wave in general? A plane wave is a wave that propagates in a certain direction such that within a plane that is perpendicular to the propagation direction, the field is the same, has exactly the same phase. So in this case, assume there is an electric wave that propagates along the x direction, okay, the positive x direction. Then within the same yz plane, the field is the same. So the electric field depends on x and t only, doesn't depend on y and z. Okay, the electric field, it can point in any direction, but it's not a function of y and z. It's only a function of x, and it's only a function of time. That is the case of a plane wave. So let's look at what are the requirements for this special type of plane electromagnetic wave. So I can write E as, in this case, a function of x and t only, okay, not y and z. This is a requirement for a plane wave. Now, one of the things I can argue first is that in a vacuum, since the field, both E and B fields are transverse fields, okay, I can argue that E and B are both transverse waves, which means when they oscillate in a certain direction and they propagate in another direction, the oscillation direction and the propagation direction must be what? Must be perpendicular to each other. That's the idea of a transverse wave, right? See, if a transverse wave like this, it propagates like this and oscillates like that. Propagation direction, oscillation direction, 90 degrees away from each other. Okay, I want to show you that plane electromagnetic waves must be transverse waves. How do I show that? Well, we're going to begin with the fact that the E and B are both transverse waves, which means gradient dot E is what? Is 0. Okay, now let me expand this. Okay, gradient dot E equals 0, and since E does not depend on y, z, when I take the gradient operation, I only have to keep the first term, I partial x, that's it, dot E equals 0. Okay, now partial E partial x. If E is a certain direction, then you take the derivative, you're still in the same direction, right? It's still in the same direction. So basically this is telling you that I dot E equals 0. You see that? I is a unit vector along the x direction. I dot E equals 0. So the propagation direction, which is I, and the oscillation direction, which is E, the dot product is 0, which means E must be in a yz plane, perpendicular to the direction of propagation. That is to say, the electric field is indeed a transverse wave. Okay, it's a transverse wave. Similarly, I dot B is also equal to 0, and that is because gradient dot B is equal to 0. So we have established that both E and B are transverse waves. So if E propagates along the x direction, it can only exist in the yz plane. We might as well choose the particular orientation of the electric field to be on the y-axis. See, if it's not on the y-axis, I'm going to just rotate the y-axis until it coincides with the oscillation direction of E. So E only has a y component. That makes things even simpler. Okay, make things even simpler. So I have E y. So I can write E as x and t, and then j. J is the unit vector along the y direction only. Okay. Given that, what I want to know is, what is the direction of B? I know the direction of propagation. That is the propagation direction I, right? And E is along the j direction. This is j. What about B? Well, you probably might have guessed that B probably is along the z direction, because you got one on each, and the only one missing is z. Is that true? Well, let's see. We can relate E and B, can we not? Okay, we can relate E and B with that equation that we wrote before. Gradient cross E equals negative partial B partial t. Okay, so gradient cross E equals negative partial B partial t. Now, gradient cross E. E depends only on x, not on y and z. So when you take the gradient operator, again, you only have to retain I partial x. Then cross E. E is only in the j direction, which is written as E j. Right? So you see, I have I cross j. What's that? That's k. Isn't that k? So I have partial E partial x times k. Okay. And that equals negative partial b partial t. Right? So that tells you that the B, the magnetic field, must be in the k direction, in the z direction. So I'm going to draw the magnetic field. Okay, I'm going to draw the magnetic field in this direction. Okay, so you see there are three mutually perpendicular directions, E, B, and the propagation direction. Okay, E and B are perpendicular to each other because, like E is in the y direction, B is in the z direction. And they are also both perpendicular to propagation direction, I, in this case. So I should write I here. Okay, the unit vector along the propagation direction. As a matter of fact, we can find the orientation, the direction of propagation by knowing the E and B direction. E is along the y direction, B is along the z direction, so E cross B gives you what? Does J cross K, what does that give you? This K. J cross K gives you I. Okay, so in other words, E cross B gives you the direction of propagation. E cross B gives you the direction of propagation. This is how we find the direction of propagation using the so-called right-hand rule. Okay, because I use right hand, take E first and cross B. The thumb tells the direction of propagation. Okay, in our next lecture, we're going to continue to discuss even more details of the plane electromagnetic wave. We can see, for example, that E and B are completely in phase and their magnitudes are related to each other, actually proportional to each other. And we can also discuss just how much energy or how much power it can carry.